First of all, I am Elisa Bortolas. Just to give you a little bit of an idea of who I am, I work in Padova in the Astronomical Observatory, and I devoted so far basically my entire career to study the dynamics of stars in galactic nuclei, where we typically also find a massive or a supermassive black hole. And so, my biggest passion in this field is actually the dynamics of supermassive black hole binaries, but also I really like the formation and evolution of MRIs, which are going to be today's focus. I also work a little bit on the dynamics of tidal disruption events of stars by supermassive black holes, if any of you is interested, so we can chat also about that at some point, if we want. So today what I'm going to tell you is, first of all, I want to give you a little bit of an idea of what is an extreme mass ratio in spiral, and I will go very briefly on that because I have a lot of stuff to tell you about supermassive black hole binaries. But I will start with extreme mass ratio in spirals, that in short we call MRIs, okay? So what are those MRIs? Well, when we have a massive or supermassive black hole, typically in the center of a galaxy, that for LISA purposes is going to be from 10 to the 4 to 10 to the 7-ish solar masses, then we also have typically a stellar population around this black hole. And this stellar population also contains stellar black holes, neutron stars, and white dwarfs that are named typically compact objects. Those objects are interesting because when they get too close to the supermassive black hole, they typically, except for some white dwarfs, but they typically do not get ripped apart. Instead, they start emitting gravitational waves, and they in spiral on the massive black hole through the emission of gravitational waves. This, of course, is interesting in the context of LISA because those are sources that we are going to be able to detect. Well, if we want to define the mass ratio of those MRIs, so the ratio of mass between the smaller object and the big black hole, we are typically in the range of 10 to the minus 3 to 10 to the minus 6, but they can go all the way down to 10 to the 9 if the small object becomes then a brown dwarf. There are studies about that. And the interesting thing for LISA is that extreme mass ratio in spirals can undergo tens or hundreds of thousands of cycles of orbits inside the LISA band. So they can really act sort of a probe of the space-time around the massive black hole. And this is amazing because we are going to accumulate a lot of signal and get a decent signal to noise to understand what is the black hole mass precisely, its spin, its distance, and also perhaps the properties of the surrounding environment. And also this is going to be a great opportunity for us to make a test of general relativity. So I think this is a really interesting astrophysical innovation that will come with LISA. So here is a plot that I think you have already seen quite some time. This is the sensitivity curve of LISA with many different sources that are written here. And those red short lines are simply the MRI harmonics of just one single extreme mass ratio in spiral, because differently from many other sources that are typically pretty much circular when they enter the LISA band, many MRIs, according to our understanding of astrophysics, are going to enter the LISA band with already still some residual eccentricity of the orbit, so they emit different harmonics that show up in the band in this way, okay? And now, what I'm going to tell you, which is basically also my great passion in research of this field, is what are the formation mechanisms of MRIs. Actually, I don't really have time to go into much detail, but I will tell you a little bit about what is the main mechanism and hint a bit on the others. So, what is the main mechanism that we believe produces those sources is two-body relaxation. I think you've heard already something about two-body relaxation yesterday from the great lecture of Manuel, but I'm going to start again from that. That was basically kind of the end of Manuel's lecture, to refresh and like really stress some points that are important for me. So let's see, say here we have our galactic center. We have at the center our nice massive black hole. Okay, and then we have a lot of stars, stellar black holes. We have all our objects right around. And if we take just a random star, it will typically do some sort of Rosetta orbits around the massive black hole and evolve, like go on this way. Of course, the star moves under the potential of what is the massive black hole gravitational field, but also the potential generated by the stellar population. This becomes more and more important as we go further from the massive black hole. However, the stellar potential is, of course, not smooth, just because stars are sort of, we can think of them as point masses. It's not that we have a continuous medium. And so, this orbit of the star that moves around nicely feels this granularity of the system, and so this means that its velocity, or if you want also its energy, to be even more precise, can change a bit due to the little tiny kicks that it feels from the rest of the stellar population, just due to this granularity. Okay? And even if, unfortunately, I do not really have the time to go into the details of dynamics, what we can define is this very famous relaxation time scale that I think was already mentioned a lot by Manuel yesterday, which is nothing else than the time scale needed by a typical star in our system to change its energy by an amount of the order of its original energy. So delta E over E, this is the energy, modulus is of the order of 1. This happens in one T-relaxation in the space of energy. And I will define the relaxation time without a derivation here as some numerical factor times the velocity dispersion sigma of stars to the cube power divided, well, this is just the gravitational constant squared. Then we have the density of stars, the mass of a typical star in our system, the Coulomb logarithm that we typically write as log lambda, and this is nothing else than something that comes out from integrals, that accounts for the fact that this two-body relaxation effect is not induced by like a couple of stars nearby. It's induced by the entire stellar system, from the closer stars at a distance of the typical distance between stars, all the way up to the typical scale radius of our system that can be kiloparsecs. And this numerical factor is typically of the order of 10. Or we can also think about that as we can write it as the ratio, the logarithm of the ratio of the mass of the central black hole and the typical mass of a star. But it's of the order 10 for our purposes. Well, what I also want to stress is that this is not per se just a global property, but it changes as a function of the radius. If we think about a system that is spherically symmetric, for instance, we can have in the center a shorter relaxation time. As we move forward, the stars are going to be less affected by those small kicks, and the relaxation time can change. And what I can write here actually are some hand-wavy but useful scalings that I can put for a typical galaxy nucleus. To be very, very simplistic, let's assume that our nucleus is what we call a singular isothermal sphere. You don't really need to understand what it means if you don't know, but what is interesting is that the density scales as the radius to the minus 2, okay? And another thing is that since near the black hole, the velocity dispersion is basically Keplerian, we can write it as some numerical factor times the G mass of the central black hole divided by the radius. So this just scales as r to the minus 1/2. Can you see it? Okay, I will just write it down here. Proportional to r to the minus 1/2. Okay? So if you just plug in those dependencies, what you can find in very simple terms is that the relaxation time in this simple nucleus we just built scales as r to the minus 1/2. Okay? Because you have the sigma to the third power, here you have the rho, you plug in those dependencies. So it's a simple algebraical game. But why am I stressing so much this relaxation time scale? Well, because this relaxation is what can actually make an object that was previously going around safely far away from the black hole and push it on an orbit that is so eccentric that basically gets close to the black hole and becomes an extreme mass racing spiral. Okay? Is it clear so far? Yeah?
Can you speak about relaxation? When you speak about relaxation, usually there is some initial excitation and then a relaxation to equilibrium. Can you clarify what is this in this situation? What is this equilibrium and this? I mean, that's what I have in mind when I think of relaxation.
Right. Okay. So yeah, relaxation in astrophysics actually, just because you have this granularity, is sort of always at play. Okay. So the system can reach an equilibrium configuration. For instance, near the black hole, it can start from all sorts of different density profiles, and eventually it will become a power law that is typically r to the minus 7/4, which is not so far from r to the minus 2. But then, just because the stars continue kicking each other a little bit all the time, it's not that at some point they stop. So the system always evolves. Maybe a tiny bit. Maybe in the beginning was evolving like crazy, and then at some point it reaches near a steady state, but it's never a totally perfectly steady state. And even when you reach, for instance, an equilibrium with a power law of rho of r near the massive black hole, what you are going to see is that the normalization of this density profile tends to drop, just because, in a way, it's like the black hole acts as a heat source in the system and just makes the stellar population expand its radius, so the density drops. So relaxation in this specific context is never perfectly achieved.
But then it is with respect to the kick, the single kick that maybe two stars undergo when they are close to each other.
Yeah, even when they are far, like it's the accumulation of all kicks at different distances that each star feels as a result of all the other stars. Okay? Is it more clear? So I just delete this thing. Okay, so this is interesting, as I mentioned, because this effect can make, for instance, a stellar black hole that was previously on a nice kind of a spherical orbit eventually get on a very eccentric orbit, and then the EMRI happens. And what happens when we have the EMRI? We have our object that was initially on a very elongated orbit, then slowly it tends to circularize, it becomes less and less eccentric, the semi-major axis shrinks, but not as fast as eccentricity, And at some point, we have something like this. So this is a typical representation of memory in this framework. What we miss in this context is that the relaxation in the space of angular momenta, so in other words, in the realm of eccentricity of stellar orbits, is much faster than relaxation in the energy space if our eccentricity of the orbit is very large, so if orbits are very elongated. And why is that? Well, if we write down the, this is the angular momentum per unit mass squared of a typical star in the system. G, mass of the black hole, times the semi-major axis, times 1 minus the eccentricity squared. Okay? And if you want to change the angular momentum of this star by an amount of the order of itself, so delta J squared divided by J squared is nearly equal to 1, well, if the eccentricity is near to 0, the time we need is exactly, or not exactly, but very close to the relaxation time.
I don't know why.
Because too boring. And instead, if the eccentricity gets very large, this means that the star has such a small angular momentum that it's very easy to change it by an amount of the order of itself, just because it is small, just because the orbit is very eccentric, and that apocenter, the star or stellar black hole is nearly at rest, so just a tiny kick can completely change the orbit. And so this implies simply that if we want to write the relaxation time scale in the space of angular momenta, this would be pretty much equal to the relaxation time in the energy space I wrote here, times 1 minus E squared. Okay? Because the factor that makes the angular momentum smaller is just this thing here. Okay? But why am I telling all this to you? Well, let me just, maybe I can, what can I delete? I can write here. Okay. I'm telling this to you because we want to make an emery. And an emery, as I mentioned to you, can be brought close to the black hole by a two-body relaxation process. But also, the emery needs to undergo many orbits around the black hole to be detectable by Elisa, because if it only undergoes one single orbit and then either it escapes or it directly accretes onto the main black hole, we are not going to have a decent Elisa signal to be able to spot the emery. So we want to accumulate many cycles. And two-body relaxation can basically quash away any spiral that just started. So if my orbit became very elongated, I get close to the black hole, I dissipate some energy, I go farther away, and then two-body relaxation again moves my orbit, I cannot make an emery. Okay? So what we need to compare is this relaxation in angular momenta with some relevant time scale for gravitational wave emission. In this context, possibly the best time scale here to use is the circularization time scale due to gravitational wave emission. That is basically the eccentricity of our object divided by the change in eccentricity as a function of time just due to the gravitational wave emission. Okay? And so this is a quantity I can write down, even if, of course, maybe I have it here. I don't remember it. Yes, is 15 over 304 c to the fifth, e to the fourth power, 1 minus e squared to the 5 half, then divided by g to the cube, the reduced mass of the binary and the mass squared. This is just M1, M2, where those are the components of the binary, divided by M1 plus M2. I think you encountered it already yesterday. So what is interesting here is that the scaling is to the a to the 4th power and 1 minus e squared to the 5 halves. Okay? And so basically, if we equate the circularization time to this two-body relaxation time in energy space, we can get a dependence of like basically a separatrix. And on the one side, we have two-body relaxation that dominates farther away from the massive black hole. And on another side, we have a gravitational wave emission that can make efficient MRIs. Now, I don't want to bring around all numerical factors. You can maybe trust me if I tell you that we need A to scale as 1 minus e squared to the minus 3/7. So this I just put equal this to this, okay? And I get something that is, if here is 1 minus e, that is basically 1 minus e squared also in the limit of high eccentricities. And here I have the same major axis. I get a function that is something like this. But then I have another important thing, which is the black hole horizon, which is something like this, because below a certain pericenter, which is the semi-major axis times 1 minus the eccentricity, we are at the ISCO, or any of your favorite places where the black hole can be considered to be lost. In a way, the stellar black hole that is in spiraling can be lost. And there is the intersection between this line that divides relaxation dominant and the gravitational wave dominant, that is a typical semi-major axis below which we expect most of MRIs to come from. And this is typically of the order of 10 milliparsec. You can see it's a very, very small scale, okay? 10 milliparsecs. Okay. Yep. Then, what do we have here? So maybe, do you have questions so far? Yes?
Is this for the order of magnitude 10 milliparsecs? How does this translate in terms of the size of the black hole itself? Are we at 100 m, 1000 m? I don't know.
Okay, I think we are at a few. This I have to check it out. It's not something I'm used to think about, but we should be at like 50 or 100-ish.
Okay.
Well, 10 to the minus 3, 10 to the minus 2. For a black hole of 10 to the 6, we have a Schwarzschild radius, which is 10 to the minus 7, or 10 to the minus 6, I think. 5, 4. No, maybe we're more like 1,000, actually.
Yeah,
okay. But I need to remember what is the, in parsecs, the Schwarzschild radius of a black hole of 10 to the 6. Maybe some of you is very fast in making the calculation. But in terms, instead, I can tell you in terms of what is the sphere of influence of the massive black hole, which is the region where the potential of the black hole is the dominant to determine the evolution. We are at a very small scales because typically, for instance, for the Milky Way, we are at roughly 3 parsecs. And here we are at 10 milliparsecs. So we are at much, much smaller scales. Okay.
But so, am I correct in understanding that it's the relaxation process that will bring things very close to the black hole, and only then the MRI system will use gravitational waves to spiral inwards?
Well, to be fair, the stellar population is always there.
Yeah.
Just in this steady state configuration, you would have some stars that come in from larger distances, some that live and go farther away. You just have a movement in between those regions.
It's that movement that sometimes lets these compact objects cross the threshold that they want then when they come close enough.
Yeah. Of course. I mean, you definitely have can have some flux in this direction, okay? Due to body relaxation, indeed. But now, for the sake of the argument, maybe there was another question, actually, sorry. Yes?
Could you go through again what are the three regions there in this diagram?
So, I mean, here we are inside the black hole horizon, so nothing can exist there. So here is the separatrix below which we have gravitational wave dominate. So the circularization time scale due to gravitational wave emission becomes faster than two-body relaxation. So those effects that make the star move and change orbit. Above here, above this line, we have instead the two-body relaxation that is dominant, okay?
Okay, but then you
and then I define this separatrix here, which is basically the crossing of this line I just defined with the Schwarzschild radius, okay? And I wrote down those milliparsecs. And yeah, this is a good question, because basically all objects that maybe change orbit here and then they start moving typically horizontally just because of the fact that angular momentum relaxation is much faster, so they change eccentricity rather than semi-major axis, then they end up inside the horizon of the black hole, but they didn't have the time to undergo many cycles. They just basically plunge into the black hole. And so those are not sources that are going to be interesting for Lisa. While if you are below this semi-major axis, then once you start moving around due to two-body relaxation, at some point you start moving horizontally, at some point you can reach this region, you would start moving parallel pretty much to the line of the Schwarzschild radius, and eventually you just enter the horizon and your gravitational wave emission stage.
Why parallel to that line?
Well, this is an approximation that is not exact, but if you just use, I don't know, Peter's equations, what your favorite tool to understand the orbital evolution of a binary due to gravitational wave emission, you see that the change in eccentricity is much faster than the change in semi-major axis of the object. So you can simplify the thing saying that you move in a line of constant pericenter. So it's like this. You keep the pericenter, let's say it's this one, fixed. Initially you have a very large orbit, then you make it shrink, but you still pass through here. It's not a perfect approximation. In fact, you also shrink the semi-major axis much more slowly. Okay? Is it fine so far? So now, instead, we are. What I want to do is to estimate what is. Oh, sorry. Yes.
Sorry.
Please.
There is a way to determine the fraction of these direct plunges in respect to the, let's say, MRIs that.
That manage.
Yeah, that have many orbits.
Well, of course, but I mean, there is a way that I don't personally know any very simple back of the envelope estimate. I didn't prepare it for now. If you do all the complex, numerical studies, of course you get a number. Okay. We are typically the plunges are more abundant, just because the stellar distribution, as we define it, means that we have many more stars at larger distance than close by. So in this graph, most of the stars live far away, and so it's much easier that they just cross in this way. So the ratio of plunges over MRIs, I would say, can be of order 100. But then it really depends on your favorite study. Can be tens, can be few hundreds. Depends if you want to be optimistic, pessimistic. What is your favorite way to compute the separatrix here? Because what I made is, of course, kind of simplified, and you can go much more into detail. Okay?
Yeah.
Okay, now the final thing I want to do is to make an estimate of what is the typical rate in the most simple scenario of MRIs. So how can we do? this? Well, let's think for simplicity about our galactic nucleus. So let's take it as a prototype for Lisa Emrys. And so I said that this separatrix is at about 10 milliparsecs, okay? Then I can write here that at the mass enclosed in stars or stellar black holes and so on in 10 milliparsecs in our Milky Way is of the order of, very order of magnitude, 10 to the 4 solar masses, okay? And since due to dynamical friction, we have that stellar black holes accumulate very close to the massive black hole, we can make a very sketchy argument and say that all this mass is in stellar black holes. And now, how do we compute the Emery rate for a Milky Way-like galaxy? I give you a hint that gives you the answer, but basically. What happens is that when an object is in this region, so below this separatrix, within a relaxation time scale in energy space, it would have all the time, even if it starts from eccentricity 0, to move around this region. So once in a relaxation time, it would end up in this region here, okay? So what should we do to compute the Emery rate? Now that we know that in a relaxation time, we span all the range of eccentricities in this realm. Yes?
I was going to say, if in relaxation time we span that entire range, and we know that the relaxation time is related to that radius that they're at, and we say we can assume basically that entire mass is stellar mass black holes, so we can say that's about the number. We just have to figure out. I know we need all of those numbers and put them together in some way. I can't give you the actual process, but I know you need those three.
Okay, that's pretty simple because let's convert these mass in solar masses into a number of black holes into this radius. 10 milliparsec. Should be, let's say, each black hole is 100 solar masses, for simplicity. We have 10 to the 2 black holes, right? 10 to the 4 solar masses, 10 to the 2 black holes. And then all of them, in a relaxation time, will enter this region. So the event rate for Emerys in our Milky Way-like galaxy is simply the number of objects in this region divided by the relaxation time. This relaxation time is of the order of 10 to the 10 years, so nearly close to a Hubble time for our Milky Way. So our Emery rate would be 10 to the 2 divided by 10 to the 10 years is 10 to the minus 8, per year. Okay. And then let's extrapolate and make an estimate of the Emerys that Lisa will see due to all galaxies that can be observed by Lisa. Okay? Lisa can see Emerys up to redshift 2 or 3. Let's be here a bit optimistic. We were a bit pessimistic here, so let's counterbalance. Let's say that Lisa can see all Emerys up to redshift about 3. Okay? We have that the volume in gigaparsec cube, moving gigaparsec cube up to redshift 3, maybe some of you has an idea. Cosmologists, is of the order of 1,000 co-moving gigaparsec cube, okay, 10 to 1,000. And then the density, the number density of Milky Way-like galaxies in our universe is of the order of 10 to the minus 7 per co-moving gigaparsec cubed, okay? Then if we multiply, what we have to do is the event rate of Lisa events per year, the number, is equal to the event rate for a Milky Way-like galaxy, the number of Milky Way-like galaxies, the density of Milky Way-like galaxies in the universe, times the volume that is observed by Lisa, right? So we have basically 10 to the minus 8 times 10 to the 3. Oh, sorry, no, I did something wrong. No, I think there is something wrong here, because this is 10 to the minus 8, sorry. Sorry, this is 10 to the 7, okay. It's not 10 to the minus 7. It would be a bit too little. Times 10 to the 7 galaxies, like our Milky Way, per moving gigaparsec, times 10 to the 3. So minus 8 plus 7 is plus 1, plus 3 is 10 to the 4, right? To the to the 2, yes. 10 to the 2 Emrys. I mean, Lisa Emery rates have an incredible range of orders of magnitudes for estimate. We go from 1 or less than 1 to 1,000. But we're in the middle. So maybe we didn't go too wrong. Yeah.
Just two quick questions here. In this rate calculation, is there no 1 by 1 plus z factor?
Oh, well, what we did is, of course, if you want to do the calculation properly, you have to account for many more things.
Okay.
This was just the simplest, let's say that it arrives instantaneously, that like the simplest you could do, just to have a very, very rough order of magnitude. Of course, it's not precise, but we didn't go too wrong.
Okay.
So that was the idea. But that's right.
Fair point. And also, I should have asked this before, maybe you had clarified it. The density of the field, right, goes 1 over r squared. Shouldn't that be the number density, and you'd expect a different mass spectrum? Like you'd expect maybe heavier stars closer to the black hole. Again, is this a back of the envelope kind of a calculation, and this is like a simplification? Is that what's happening? Okay, just want to make sure.
Yeah, no, absolutely.
So you'd expect more massive of those background field closer to the star, closer to the massive black hole.
Yeah.
Okay.
Yes, and that implies basically that the most likely object to be detected by Elisa is stellar black holes that are maybe a bit also heavy. Just because those tend to segregate to the center due to dynamical friction, they undergo this mass segregation. So they really accumulate near the black hole. So they are more likely to be inside these 10 milliparsecs, which is a rough scale. Again, you can find different estimates in the literature, but it's order of magnitude. And then those are more likely to become Emrys. And they give us a louder signal, since they are more massive. So we are all happy. Okay, I'm already very late for supermassive black hole binaries. But I will try to still not go too fast, because otherwise we cannot understand anything. Maybe I'll just erase here. So the framework here to move to supermassive or massive black hole binaries in the LISA framework, I think it's known to all of us. And it's the fact that galaxies aggregated through repeated mergers. They start from smaller galaxies in the beginning of the universe. They build up their mass through mergers. And also we have evidence from quasar observations, for instance, that many massive black holes were already at the center of those galaxies since the beginning of the universe, since redshift 6 or 7 or maybe larger. So if we combine those two things, what we can have as a result is that often, when two galaxies merged, two massive or supermassive black holes found themselves inside the same system. And if those two black holes manage to shrink their separation down to the scale at which gravitational waves become efficient and they make them merge, then we can observe massive black holes with LISA. Okay? Let me just finish this thing so I have a little more space. Okay. Well, LISA binaries, again, massive black hole binaries. This is the LISA sensitivity curve. It's beautiful here because you can really see that they can really go through the sensitivity curve and stay there. Here is the time to merger. So some sources can enter the LISA band really weeks before the actual final merger. We have all the time to see their evolution, to accumulate signal to noise. It's beautiful. Yes?
Just what's the gray on the left?
Sorry?
What's the gray area on the left?
Oh, this. Oh, yeah,
Okay.
I think, yeah, you cannot really see beyond this, yes. Yeah, and so, very interesting. And this is even more interesting, well, why? Here what I'm showing to you is the mass function of black holes, of all masses. We go from 10 solar masses all the way to 10 to the 10. Here we have our beautiful stellar black holes. Manuel yesterday told us a lot about them. They are observed in LIGO Virgo, this and that. We know how they form. We know more or less how they evolve. And we know more or less what is the stellar population. When we go to the very, very large black holes, 10 to the 8, 10 to the 9, 10 to the 10 solar masses, electromagnetic observations are doing a decent job in telling us where they are, how many of them we have, at least in the closed universe, so we can put down a mass function. However, as we go to this intermediate mass regime that we can say starts from roughly 10 to the 2 all the way to 10 to the 5-ish solar masses, then it's very hard to observe the electromagnetic emission from objects in this mass range. Of course, it's not the black holes that emit, it's just the gas falling on them. But it's very hard to spot them electromagnetically. So we really don't have a clear idea of how those massive black holes, how many of them are there, what is their occupation fraction in galaxies. And why this is important? Well, because LISA is going exactly to cover this intermediate mass black hole mass range, going from a few times 10 to the 3 or 10 to the 4, all the way to 10 to the 7. This is a realm where we really don't know much about black holes. And the other very beautiful thing of LISA is that probably you've seen already this waterfall plot. If here we have the mass of the black hole binary that is going to be observed by LISA as a function of redshift, and those lines are lines of equal signal-to-noise ratio observed by LISA. We have here 1,000, here 3,000, and we go to smaller and smaller, but still observable. This graph tells us that we are going to observe massive black holes in the intermediate mass range, basically up to the beginning of the universe, up to redshift 20 or so. So we are going not only to observe mergers of black holes in this less known regime, but to observe them all the way up to the beginning of the universe, where we had the seeds, perhaps, that grew and produced the more massive black holes we can observe today in the local universe. So for this, LISA is going to be a game changer, okay? But of course, if we want to work well in preparation for LISA, what we need to do is to try to understand what happens to two supermassive black holes that were brought together due to a galaxy-galaxy merger. So what is the delay between the galaxy-galaxy merger and the merger of the two black holes themselves, if it ever happens? Because maybe something happens and it cannot ever happen. So what is the time scale? And those processes, how do they change the distance, the semi-major axis of the forming binary, its eccentricity, the spins of the two black holes? All those things are going to be actually observed through LISA, okay, somehow. Or LISA is at least going to give us some hints. So we want to be prepared and to make good predictions. And what we need to do is to understand really the path to coalescence of LISA massive black hole binaries. So let's start from a very large scale. Here I put the distance scale for a massive black hole binary that is typical of LISA. So two black holes of roughly 10 to the 6 solar masses. Below you find as a reference two black holes of 10 to the 10 solar masses that are not going to enter the LISA band, but could be relevant, for instance, for pulsar timing array studies. So you can see that those distances vary, but the processes at play are similar, okay? And so at large scale, we have, first of all, the galaxy merger and then dynamical friction. We are going to cover it in a second, but you've already heard about it yesterday. And then at some point, for Lisa binaries close to parsec separation, when the two black holes reach this separation, dynamical friction is no longer efficient, and you evolve and make the binary shrink through three-bond interactions with stars coming close to the binary. We are going to go into detail. And then if there is some gas around, a disk of gas, this can also torque the objects and make the spiral change, maybe go faster or somehow, sometimes maybe even slow down. And finally, when we enter milliparsec scales, typically for the Lisa band, we can have gravitational waves start dominating, and then we end up with the inspiral and coalescence. That is very straightforward. And by the way, this scale at which stellar interactions start to be effective is the typical scale also at which we can consider a bound Keplerian binary of two massive black holes to be formed. Because at further scales, the amount of mass in stars or gas or dark matter, we can think of it as inside a sphere centered on each black hole, is much larger than the mass of the black holes themselves. So it's like each of them evolves independently without even knowing the other is around. While at this scale, more or less, finally, a bound binary forms, they see each other and they start evolving really as a binary system that you can study through Keplerian equations you all know, okay? So, okay, let's go into the dynamical friction framework. Well, what happens with dynamical friction? We can think of it in a very simplified way that maybe is not 100% correct, but gives us an idea for this context. So let's say we have a massive body. Can be our massive black hole, can also be a stellar dense cluster, whatever you like. In this context, we say it's a massive black hole that travels and moves through a field, a homogeneous field of stars. When the black hole passes, it attracts stars that are around it, right? Just because of gravitational pull. But by the time the stars try to reach the position of the massive black hole, the black hole, due to its velocity, has moved a little bit further. So it's like there is an accumulation of stars, an overdensity, or also could be dark matter particles, at the back of this black hole, and this overdensity, of course, slows down the black hole because it exerts also a gravitational force. Be careful that this is just a local approximation of the dynamical friction, the idea of dynamical friction, and this is basically the backbone of the idea of Chandrasekhar. But there are papers by Weinberg and Tremaine that say that this process is so much more complex. The body that is heavier makes orbits of stars resonate with the orbit of the massive black hole. Is like the black hole is like when you play a drum and the skin of the drum starts undergoing different oscillations due to the harmonics of the drum. So the galaxy would be the same way as it is beaten by the black hole, and all those resonances act in a weird way to slow down the black hole. But the mathematical framework is a nightmare, and I don't want to cover it here. The other thing I want to tell you is that dynamical friction is the most efficient when the velocity of our massive object is roughly the same as the typical velocity of stars that is going through. So this is typically encapsulated in the sigma, in the velocity dispersion of stars in the system. And you see that the force of dynamical friction increases linearly with the velocity of the black hole at small velocities. It has a peak roughly at the velocity of the stars in the system, and then it goes down. Just because if the black hole is too fast, stars don't even have the reaction time to see that the black hole has passed. It is so fast that the interaction time is so small, they just ignore its passage, and the wake behind the black hole cannot be formed. Here I'm covering basically the situation if we have a field of stars or equivalently dark matter particles that are collisionless. But if you want to study the gaseous case, so the black hole that goes through a mainly gaseous medium, basically your reference velocity is the velocity of the black hole over the speed of sound of the gas you are thinking of. And what turns out is that, again, the maximum interaction is when the black hole has a velocity that is close or a few times the speed of sound of the surrounding medium. So it's slightly supersonic, okay? And the equations that govern the two processes are very similar. So it means that it's a kind of a common process, okay? And here you can see what happens in the case of gas, for instance. If the black hole moves too slowly, this is just at the Mach number, basically the overdensity around the black hole does not manage really to go at the back because the black hole is kind of slow, so also the gas piles up in front of it, so we don't really have a decent braking effect. But when the black hole starts becoming more and more fast, like a little bit supersonic, then all the gas that piles up due to the passage of the black hole piles up at the back. So it has really a dragging force on the black hole and slows it down. When we go way too fast, then again, gas doesn't have time to respond to the passage of the black hole, and you cannot even have time to accumulate a fraction of gas to slow it down. So that's it, basically. Okay, and this dynamical friction is nice because if you put together all the formulas, I'm not going to go through the derivation. I have it if you're curious. Just ask me, I'll give you the slides. There is everything. I can give you books. You can compute everything. It's fun if you want. I don't have it now. But what comes out from the dynamical friction theory is this very nice, easy peasy formula that tells us, okay, what if I have a massive black hole of a given mass? Here I put the 10 to the 7 solar masses, moving into a galaxy that has a velocity dispersion of stars of 200 kilometers per second. This is a very typical galaxy, could be our Milky Way. And it starts to spiral at a given separation that here I put at kiloparsec scale. Here it's just scaled over kiloparsec. Well, how long does it take? Since this Coulomb logarithm is the same we encountered before in the framework of two-body relaxation, and the gain is of the order 10, then the time scale for our black hole to reach the center would be 0.8 gigayear. You have to divide this number by 10, which is the Coulomb logarithm. So in the 0.8 gigayear, a massive black hole of 10 to the 7 solar masses would reach the center of a galaxy similar to our Milky Way if it starts from basically the edge of the bulge of our Milky Way, which is roughly 1 kiloparsec. Okay? So this is a very easy formula. You can write down your favorite numbers for your favorite galaxies, favorite black hole that inspire. Of course, it's a simplistic approximation. It's not 100% correct because, of course, reality is more complex than our simple mathematical formulas. First of all, we have galactic tidal stripping. So when we have a galaxy-galaxy merger, let's assume now for the sake of the argument that we have a bigger galaxy and a smaller galaxy, 1 to 5, 1 to 6 mass ratio, that merges with the bigger one. Then in the beginning, the dynamical friction is going to be felt by the entire galaxy mass that entered the bigger galaxy. So we have, sorry, maybe I can do like this. We have a bigger galaxy. We have this smaller galaxy with the black hole at the center. And then in the beginning, we have all the galaxy mass that feels dynamical friction. But as this galaxy inspires, it also loses mass from the outskirts because it's streamed by the basically the effect of the density profile of the main galaxy. So it becomes more and more smaller, and also it loses mass. So we would have a mass of the intruding object that is undergoing the friction, that is a function of time, okay? At some point, if the galaxy is not too dense, what we would have is just a naked black hole that lost all the surrounding stars that previously belonged to this smaller galaxy, and the black hole spirals. But of course, what we would have is to tweak and change this dynamical friction timescale prescription accounting per the tidal stripping. People has done that. There are formulas, there are equations, there is stuff. It's too complex for now. But if you are curious, there are ways to do that. And also there is a lot of realm for investigation. Yes?
Like how long does the stripping take? Like is it like is it a few orbits, 100 orbits?
To make it to the center. Well,
to strip it.
Oh, it really depends. It really depends on the properties of both your bigger and the smaller galaxy. If the smaller galaxy is very, very dense and the bigger one is not so dense, it can make it basically all the way to the center. But if it is the opposite, you can just lose the entire thing in one orbit. I mean, it can be very different. You really... as a rule of thumb, you can basically compare the densities. Then, of course, you can go into more detail, but yeah. So this was one limitation. Another limitation is that, of course, galaxies are not perfectly smooth, nice balls of stars, okay? There can be other things going on in the galaxy. For instance, let's assume the galaxy is clumpy. It has some clusters of stars and gas that have a mass that is close to the mass of the black hole that is trying to spiral. If we have the black hole that encounters one of those massive clumps, it is scattered through gravitational wave interaction. And we can have, here is an example of actually a simulation near a galaxy. Those should be kiloparsec scale. Sorry, I forgot to put the axis. But this was a black hole that was trying to spiral in the center of a galaxy. It got a kick from a clamp. You can see clamps in this galaxy. And then it was basically ejected far away from the center. And in this case, it didn't even manage to go back to the center. And the same torquing mechanism can act, for instance, if there are galactic bars that do not make the density profile so smooth. Also, it could be that the galaxy has a weird shape, is undergoing a galaxy flyby, it's adjusting dynamically. So what can happen in more complex situations is that if we write the gravitational torque due to dynamical friction as a function of time, for instance, can be, I don't know, like here. And then we write sorry, it's this one, PDF. And then the gravitational torque due to, I don't know, the presence of a bar could be that in some cases is larger. So basically, it is as if the object would only move in response to the bar, and the dynamical friction is a tiny correction to it, meaning that this time scale is not going to be really correct, okay? Okay, and then finally, another thing, oh, yes, please.
In this example here, with that diagram,
yeah.
I guess we're making an assumption that the orbital plane of the two black holes is along the same plane as that of the galaxy, of the primary galaxy.
Yeah, yes.
But that would be the most rare of cases, right? You'd expect it to be random mergers, right?
Yeah, I mean, I think the disk can torque you. I mean, the presence of the disk would torque the orbit inside. It's just a pull. It tends to align. Then if it happens or not, then it depends on your system, I guess. But that's absolutely true.
Because I would have thought, because you said that the Keplerian effect takes place only like at a parsec, right?
Yeah.
So, I mean, that means, galaxies are like 20 kiloparsecs, if I'm not, something like that, right? So you don't expect any Keplerian effect. I assume you mean there. So I wouldn't have expected the gravity to have an effect until they're already merging, essentially, is what I would have thought.
Yeah, so no, that's true. So it depends, of course, on the shape of your galaxy. If you have two elliptical galaxies, then you don't care. If you have a galaxy, because if it is a spherical, the density is pretty much the same order of, more or less, let's say, at all points. But if instead if you have a much denser disk of stars and gas, and your orbit is initially outside, then it would take longer, of course. And it is true the disk tends to torque you down so that you tend to go into the plane, but the time scale over which it happens can be long, depending on the properties of your system. So this, of course, is a simplification of the theory. Yes?
Just to follow up on that, yep. Everything is true, but you need to remember that as long as the two nuclei of the galaxies haven't merged, the dynamics of the black holes just is stuck with the dynamics of the galaxy, right? So I think that the large-scale torques by the disks will not act on the black hole until the nucleus of the galaxy hasn't been completely erased. And this usually happens unless you have a minor merger, where you have a small galaxy that is plunging into the halo of the big galaxies and is stripped away. In that case, the black hole will lose its shield and it will start moving according to the galaxy field. So then it can feel torques. But in this case, it would be too far from the center to reach the nucleus in a Hubble time. So dynamical friction would be inefficient. Because this is a small galaxy, the black hole inside is likely small, and dynamical friction scales with the mass of the black hole. When you are inside and you have the merger of the two nuclei, then the black hole is released into and will start moving in the innermost region of the galaxy. So even though you are coming from a random motion, from a random direction, and you have the merging of the two nuclei, it is essentially, you can think of the black hole that must be released within 1 kiloparsec scale distance from the center. And there, you can have this torquing action that can dump down your orbit, and anyway, it can act on the motion of the black hole. But it's still kind of a local physical process.
Another thing I just realized is that the halo, no, you can use like the halo, dark matter halos need not be this, they can be more diffuse and like a sphere. So that's where it makes even less of an impact.
Yeah. Dark matter halos are typically less dense, but they still have an effect on, dynamical friction is also due to the dark matter, as far as we understand dark matter. But probably it's the case. So, yes, so be careful, mindful about those complications. And really connected to what you just said, we can have a disk galaxy, but most importantly, a galaxy that has a net rotation. Because this derivation was made thinking about a galaxy that didn't really have a net rotation, but just the stars were going into random motions. It would be dominated by velocity dispersion, so just a ball of stars. Instead, if we have a disk galaxy and the stars tend to have a rotational velocity, as the case of the disk of the Milky Way, for instance, then the spiral changes due to this. Because, for instance, if your initial object, even just inside the plane of the disk, is initially pretty eccentric, the dynamical friction acts in a way that it tends to circularize the orbit of your inspiraling object. So even if in the beginning, typically galaxies merge on hyperbolic orbits, so they are very eccentric, it could be that by the end, when the black hole with its surrounding nucleus made it to the center, it became pretty much circular. Just because dynamical friction, like the wake, basically is in front of the black hole of your massive object at the periapsis. So it makes our massive object go faster. And instead is at the back, the wake is at the back at periapsis. So those forces that are opposite to each other tend slowly to make the orbit more and more circular. And another thing I want to tell you is that if we are inside, again, the plane of a disk, here is the disk. Here we have our massive body. And maybe we start with a more circular orbit this time, but we are counter-rotating. So the orbit of the angular momentum of the massive body is opposite to the angular momentum of the disk of stars, for instance. Then the opposite happens. So it tends to excite eccentricity in the orbit of the massive object until at some point it basically reaches a pretty high ellipticity or eccentricity of the orbit, and then it reverses its angular momentum, so it starts rotating in the direction of the stars. So this is interesting because this evolution of eccentricities from very large scale to small scales can propagate all the way down to the gravitational wave emission stage. So we want to keep track of it to see if LISA will detect any residual eccentricity in the band. Okay? Good. So why did I tell you all this? Well, because if we think about a very nice elliptical galaxy, dynamical friction works well. But LISA is going to mainly observe galaxies, massive black holes that are in galaxies at high redshift and of low mass. Low mass galaxies, even in the local universe, are often very irregular. They have weird shapes, they have clumps, they have a bar. So dynamical friction cannot be the best approximation, can be too much of an approximation. If we go at even higher redshift, it becomes worse because the galaxies didn't have time to really settle down to a virialized state. So they can still be very messy. And so this is just to put things a bit in the context of LISA. Okay? Okay, let's move to the smaller scales, finally, to the stellar hardening. So what I'm showing here is the distance between two massive black holes as a function of time. And what you can see here is that at large scale, you really see the effect of dynamical friction. Then at some point, the separation between the two objects drops so fast. And then it starts to evolve slowly again. And here we are going from separations of kiloparsec scale. We start reaching, we have this strong drop from roughly 10 parsecs to a fraction of a parsec. And then we continue evolving, hopefully all the way down to gravitational wave emission. So what happens here? First of all, we have that in this region, more or less, for 10 to the 6 solar mass binary, the binary actually forms, the Keplerian binary. And then dynamical friction starts acting together with stellar hardening. So in this region, both processes, dynamical friction and stellar hardening, I'm going to tell you what it is in a second, they act together. So the shrinking is super efficient, and also stellar hardening is the most efficient when the separation of the binary is larger. So this is just a boost in the evolution. It goes down very fast, meaning that if you want to electromagnetically spot binaries, it is very unlikely to find them here. Just because their evolution goes so fast, you don't really have a good chance. And then from this scale, pretty much, dynamical friction is no longer efficient. Stellar hardening starts to be less and less efficient, so you have a slower evolution. But what is this freaking stellar hardening? Well, what we have is that we have our binary, okay? And then we have that a star randomly goes close to the binary just because its orbit at some point needs to intersect the orbit of the binary. And then what happens is a three-body interaction. Two bodies are the two black holes, and one is the star. And typically, if you try to explore the parameter space, making many scattering experiments, throwing stars to a binary, what happens after the interaction is, on average, typically, that the star is kicked out with a larger velocity compared to the velocity at which it arrived, while the binary, for conservation of energy, of course, has shrunk a little bit. So this process, if it is effective and many stars go down to interact with the binary, can really make the binary shrink from parsecs separation all the way down to the milliparsecs at which we have gravitational wave emission. And of course, you can even intuitively understand that as the binary separation is larger, its cross-section for stellar interactions is larger, so this process is more effective. While as the binary shrinks, the cross-section becomes tiny, so it is less likely that a star goes through the orbit of the binary and there goes an interaction. Question?
Yep.
Is it possible that passing by star slows down and therefore gives energy to the binary?
Well, it's incredibly unlikely. I mean, those three-body scatterings, I mean, the three-body problem doesn't have analytical solutions. You just have to solve it numerically. So you can have, in principle, all sorts of outcomes. But what I will tell you is that the system, for how it behaves, it tends to reach equipartition, meaning that the two black holes, the supermassive black hole binary, tends to have the same energy as the star. Since the star has a tiny mass compared to the binary, in the end, what it happens is that it gives a lot of energy to the star while the binary shrinks. And also, maybe I can, let me think if I can explain it even in a better way. Well, no, yes. Also, if, let's say that you have a binary, and then you have a star coming close, and in the interaction, you have just a brief interaction, and the star loses energy, it gives it to the binary. But then the star remains there, because its semi-major axis has shrunk, right? Since the energy became smaller, the semi-major axis shrunk. It means it's even closer to the binary. It stays there. So until you get an interaction that makes you fly away from the center, you would stay there. You can have, I don't know, you can have 1,000 orbits, but the only way to leave the system is to be kicked away. So statistically, maybe it can take a little time, but eventually the binary will give energy to the star and make it go away.
Okay.
Yes?
Thanks. You can also have a triple interaction with another massive black hole, like triplets, and it happens at this scale.
Yes, yes, absolutely. So, I mean, if we have two consecutive mergers, so we have a galaxy-galaxy merger, two black holes go down, one binary forms, and then in the meantime there is another galaxy that brings in another black hole, we can find the three black holes evolving here. And then the different things can happen. Again, we can have a very strong and unpredictable outcomes of three-body interactions, like one black hole being ejected far, typically the smaller, again, for what I said before, and the other two, since this object was pretty big, just merge straight away. There can be quasi-lead of resonances if the third black hole is at a bit larger scale, so they excite eccentricity in the inner binary, and so since gravitational wave emission timescale for large eccentricities becomes very small, this can also help the inner binary to merge. You can have different situations, but this is going to have an impact. And triples are not supposed to be so rare.
Yeah.
So this can well happen. Okay. So, okay, if you want to do an order of magnitude estimate of what happens, then what you typically have is that the binary forms when the mass in stars enclosed in the semi-major axis of the binary is equal to the binary mass. Makes sense, right? Because the stellar potential of stars around becomes comparable to the potential of the other black hole. Then dynamical friction stops to have a strong effect when the mass in stars enclosed in the orbit of the binary is close to the mass of the secondary black hole. So if the two black holes are nearly equal mass, the binary becomes bound, and at the same time, dynamical friction starts becoming inefficient. if the secondary black hole is much less massive, dynamical friction continues happening for a long time until the separation of the secondary gets smaller and smaller, but at those scales is inefficient. So if we have a very big central black hole and the secondary is 10 to the -2 or 10 to the -3, we are, compared to the primary, we are in a regime in which it's very hard to do the jump down to stellar hardening. Also, basically, because if you make the calculations, stellar hardening basically starts at the gravitational wave emission stage. So stellar hardening starts acting together when gravitational waves start to be efficient. So we have our favorite are close mass ratio, maybe 1 to 1, 1 to 10, 1 to 20, but 1 to 100, 1 to 1,000, not great for LISA, let's say. The time scales become very, very small. Then we have a typical separation, which is the hard binary separation, which is defined by gravitational constant, the mass of the secondary black hole, divided by 4 times the velocity dispersion of stars squared. And this is typically smaller than that other scale I defined there. And at this separation, I think I'm showing it to you here. No, maybe, well, I don't have it, but if you do the math, maybe we will do it in a second, what happens is that, first of all, at this separation, the binary starts hardening, so evolving at a constant rate. You have this very smooth evolution. And also the binary starts being very efficient in just kicking away stars that interact with it and making them gain a velocity that is basically the escape velocity of or larger. So those stars, is not that they go far away, they just leave the system. It's a way to produce hypervelocity stars. Okay? Okay, this I already said that we are basically at the radius of influence. Okay, this is also maybe interesting because in this phase, what happens is that...
may I ask a question for the last slide?
Yeah.
So what happens when this mass ratio is small? Like you said that it's not great for LISA, but what do you mean there?
Just the dynamic, then when the mass ratio is very far, basically dynamical friction is the only process that is effective in bringing the two black holes together, basically nearly to the scale at which we have gravitational waves that start becoming dominant. So we basically skip the stellar hardening. Just because this scale, AH, at which you have the stellar hardening become important, becomes so slow due to this dependence on M2 that you are, you basically never reach it. So you have to rely on dynamical friction at those scales to make the two black holes shrink. But dynamical friction here is very inefficient. So the time scale over which it can make the jump from parsec to, I don't know, 10 to the -3 parsecs can become many gigayears or gigayears. So it can be a very long delay.
So you're saying that this kind of systems not likely to exist?
Well, they can exist, just they might not be the ones we spot with LISA.
But what's the, well, I can understand maybe they are really inefficient, so it takes a long time to form them, so they are not dominant, but once they are there, LISA should see them, right? LISA can still see them.
Well, but LISA, to see them, needs them to be emitting gravitational waves effectively. So if you are too far away and the binary is not yet in the gravitational wave emission stage, you are not going to get any signal. You just basically have a stalled binary.
Okay.
That's, but to be fair, for the LISA band is probably, is probably not likely also because at those stages we can also have the effect of a gaseous disk that helps the shrinking. So this can come to help us shrinking the binary. And then at this scale, in this region, what happens is also due to this scattering effect, the binary basically carves a core in the density profile of stars. So here we have the density as a function of radius in the density profile of stars, and inside the influence radius of the binary, what we have is that the density profile becomes flatter just because the innermost stars were kicked out. And so this is an observable effect for big elliptical galaxies. There are observations, now they are basically all with HST, so they are pretty old observations, and they find a carved density profile in the very big ellipticals that are the ones that are more likely to have undergone most mergers. So this is an observable effect. And also this observable effect can be, well, reproduced in simulations, and also you can have a signature in the orbits of stars just because, of course, again, as for MRIs, if you have a star that needs to interact with a massive black hole binary, if the eccentricity of the orbit of this star is larger, so the orbit is more elongated, it is more likely that the binary the star interacts with the binary. While if our orbit is more circular, it is less likely, okay, for the same semi-major axis, for instance. So what you have is that after the binary has kicked out stars, you have a dominance of stars on more circular orbits inside the center of this galaxy compared to stars on more elongated orbits. And this has been observed, again, in these galaxies with a carved core, those that I just discussed. There is this, it's called velocity anisotropy, and near the center of the system, you have really a net dominance of stars on more circular orbits, just because those are less likely to get close to the binary. Okay, here I also put the derivation, for how happens this three-body interaction, but well, I don't really have time to go into this. I'm going to tell you that it's a matter of using a cross-section for the binary interaction, then putting it equal to the number of stars that can get close to the binary, and then what you get is the derivative as a function of time of 1 over the semi-major axis of the binary, if you do all the math. And this comes out from formulas. It is equal to 4 pi times the gravitational constant, the density of stars, basically at the influence radius, divided by the velocity dispersion of stars. And this, if we assume that those two properties of the galaxy don't change too much as the binary evolves, is a constant value. So this just means that those hard binaries that are the ones that are already in this efficient ejection mechanism harden at a constant rate. So yeah, if we plot 1 over the semi-major axis as a function of time, it's just a straight line. So it's very easy to model it in a way, okay? So knowing this, we can actually compute a typical time scale for the hardening process to occur from parsec separation down to milliparsec or centiparsec, where the gravitational waves become dominant. And this, if you do the math, is of the order of a few 100 million years. Well, here I put 0.25 gigayears, and all the properties I put are reasonable for a binary in the Lisa band, okay? So it's typically a shorter time scale compared to dynamical friction time. So the longer time scale in this framework is typically dynamical friction. And then, of course, you can use formulas also to study the evolution of the eccentricity of the binary as a function of time. There are papers that study it into detail. What I'm going to tell you is that in spherical systems, in spherical nuclei, you typically have that are non-rotating. Typically, the eccentricity of the binary grows due to stellar interaction if the eccentricity is already above 0.5-ish initially. While if the eccentricity of the binary is smaller initially, it tends to stay small. So you can really have a complete picture of the evolution of a semi-major axis and eccentricity due to this stellar hardening process. Oh, okay, final parsec problem. I don't think I have time for that. Well, I'm just telling you that there has been for a long time this misunderstanding for which people would say, look, this stellar hardening process doesn't work. Just because you don't have too many stars coming efficiently to the center, once you kicked out the ones that are very close, you don't have anything else that pushes new stars close to the binary, so the binary cannot interact with anything, and it will stall. It cannot shrink further. But instead, if you take a potential that is not perfectly spherical, and the orbits of spherical potentials are rosettas, they keep the same energy, so it's not that they stay far away from the center and then eventually get in. If we have a potential that is more realistic, triaxial, spherical things don't exist in nature, by the way, then you can spend a long time far away from the center, and then due to the torques that are induced by the non-sphericity of the stellar potential, you may reach the center and interact with the binary. Just by adding realism, we solved this possibility that the binary would stall and not evolve through stellar scatterings. Then, okay, here we have something about gas. This is not really my field, but I'm going to tell you that the evolution of a binary, if there is also some gaseous disk around, it's unclear. Because the initial studies started to say, okay, if we have a disk of gas, then of course the binary will be torqued in a way that it can merge faster. And there is this simple calculation made by, I think there is, oh, I forgot to put the references, Dotti et al. 15. Then what you can figure out by very simple arguments, assuming the binary is accreting at the Eddington limit, this and that, basically in something of the order of 10 to the 7 years, so 10 million years, you manage to reach the gravitational wave emission stage just due to the presence of a disk of gas. More recent studies, instead, point to the possibility that in some configurations, which are a binary of nearly equal mass, a disk that is pretty thick, the disk of gas should be pretty thick, and basically this, the presence of a disk of gas would instead make the binary expand. So, like this, terrible for Lisa, no, we want to shrink the binary. But, I mean, the good news is that I had a lot of fun with my colleagues trying to understand if this would be really a showstopper. And since basically all galaxies that have a disk of gas also have a stellar population, if we plug in also the fact that the binary is not going to evolve only with this disk of gas that expands, but also with the presence of three-body scatterings, then you still merge the binary. The maximum delay, if you are really unlucky, you can get a delay in the merger of 10 to the 8 years, but still less than dynamical friction time, so we don't care. Let's say. And then, oh, I don't want to bother you with this. These are the Peters formula. You know them by heart. I don't want to spend 2,000 years on this. Just to tell you that you know how to evolve the binary now through three-body stellar scatterings. You have the nice Peters formulas tell you how the semi-major axis eccentricity of the binary evolve due to gravitational wave emission. Bear in mind, if you have a very large eccentricity, you can shorten the spiral time by a huge factor. So bear in mind, eccentricity is important, but you have all the ingredients now to solve the evolution of binary. And here, as a time scale, I show you that if we are at 0.1 parsec separation with a binary, oh, in this case is even pretty large, of 10 to the 7, 10 to the 8 solar masses, then it can take 580 gigayears to merge. We don't like it, but we just need a pretty large eccentricity and we go again below the age of the universe. Or we just shrink the semi-major axis by a factor of 10, then we have a 10 to the 4 factor here shrunk, and then we are fine. Kick. I'm just going to say that when the merger happens, the merger product can receive a kick due to the anisotropic emission of gravitational waves. And what can happen is that the final black hole does not sit still in the center of our system, but moves around and again needs time to shrink down due to dynamical friction. And this can also help carving a core in the stellar density profile that is much larger than the one we discussed before. So this is a way to explain super large cores that are observed in some ellipticals. To conclude, let's put everything together. We can write down the residence time scale of a binary at each separation as the separation of the binary divided by its derivative of the separation over time. This is basically the time scale a binary needs to cover a logarithmic step in separation, okay? At x if you want. So if you put in the formula for dynamical friction, you have this formula for the residence time that goes with the square of the separation. You can plug in scaling relations between the, like for the velocity dispersion and initial radius of the system. And then we can do the same for stellar hardening. Stellar hardening goes as minus here and the square of the semi-major axis. We just discussed it before. So if you compute the residence time, goes as 1 over the separation. And finally, gravitational wave emission. We already said stuff about that. The residence time goes as the semi-major axis to the 4th. Let's put scaling relations in place and see, depending on the mass, different masses of the binary, how much time they spend at each distance, okay? And here we have dynamical friction, which goes as r squared, stellar hardening as 1 over r, and the gravitational wave emission as r to the 4 power, okay? Well, dynamical friction can be the dominant one, so we can reach typically the 10 to the 9, so gigayears of evolution here. But if we neglect dynamical friction, the longer time spent by the binary at a smaller scale is exactly in the transition between stellar hardening and gravitational waves. Okay, so this is where it is most likely, we are most likely to spot them through, for instance, electromagnetic searches. Yeah, this I just said. But here I'm ignoring the effect of gas. Can make this estimate go up and down by a little bit, but not much. So we can reach a fraction of 10 to the 7 for those limits, or like something around 10 to the 8-ish if we have the expansion we spoke about before. But again, the picture is pretty much this one. And then, well, if you want to estimate the number of galaxy mergers Lisa can see, you can make the easiest argument you can do, as we did before for Emrys. How many galaxies we have in the universe? 10 to the 11. The same as the stars in the Milky Way, more or less. We can say, rule of thumb, each galaxy undergoes one major merger in its lifetime through the evolution of the universe. The Hubble time is 10 to the 10 years. So we can compute the binary merger rates, assuming Lisa can observe all our universe, as the number of galaxies times the number of major mergers per galaxy in the Hubble time divided by the Hubble time. 10 events per year. This is not so far from Lisa, much more accurate estimates. Estimates can go from a few to a few hundreds. If you want to push the models, you can get to thousands, but whatever. Yeah, and here I want to conclude, just to tell you that this evolution of massive binaries is a complex process. We need to know a lot about the environment. We need to know a lot about what are the properties of our black holes, the galaxies that came in, this and that. But we have a lot of knowledge now, and we need to proceed further to really make much better estimates than the one I made for Lisa merger rates. So this is your job, of some of you. So please bear in mind. And finally, Lisa is not going to be the only player here, because we are going to be the Einstein telescope coming in some years. And also pulsar timing array observations are already finding a hint of a signal. So this means that really the gravitational wave landscape of massive black hole binaries is going to be really dissected into the tiny details in the next years. We are I would say we are close to a golden era for this. So stay in the field and have a lot of fun. I finished.
Okay, do we want one question?
Sorry, I was a bit long.
Yeah.
If you wanted to detect some of these effects from the gravitational wave strain, at what point in the strain, at what time and at what order of magnitude, like PN order, do you expect to detect these effects, if at all?
With these effects, you mean?
At least like stellar hardening. there's a time when stellar hardening, we would be observing the signal while the stellar hardening is happening, or because of gas effects, or signatures due to like indirect signatures from your environmental effects. Do you expect to detect them in your strain?
I mean, if you think about the presence of gas, I think that's more likely because this can really go down to small scales. And then there is, I think, Lawrence Zwick, if any of you knows him. He's working on those environmental effects, so how the waveform can be shifted here and there, delayed a little bit just to the fact that there is some residual gas torquing the orbit of the binary. Stellar hardening, I don't think you can really have a stellar hardening while you are in the Elisa band.
Like 2 slides ago, it wasn't like that? Or maybe I missed it.
Oh, okay, no, okay, yes. So here we have the transition, for instance, let's go here. We have the transition between the stellar hardening and gravitational wave emission. But here, even if you are starting to be dominated by the evolution, by the gravitational wave emission, it doesn't mean those gravitational waves are observable by Lisa.
Okay.
You need to go further down in distance. So for PTA observations, you can have some binaries that are still also have some impact of stellar hardening. For Lisa, not to my knowledge. Maybe there is some surprise, but not to my knowledge.
You need MBH.
IMBHs?
Yeah.
Okay.
If you have a binary MBH, then you may have some chance of getting some environmental effect because they start. Let's say that the hardening will affect the frequencies which are 10 to the minus 4, 10 to the minus 3 Hz, maybe 10 to the minus 4 more. So maybe you are close to the hand of the Lisa.
But SNBHs, they move even further to PTS side of things. Gotcha.
Okay. Well, thanks again.
Thank you.